Hello students, this module is about giving you several examples that illustrate how to evaluate integrals both involving real variables and complex valued variables using the residue theorem. Okay, so this is a very useful topic that we are going to see that the evaluation of integrals using the residue theorem is very useful. For example, in the inversion of Laplace transforms, when you encounter Laplace transforms, for example, in process control, right, process dynamics and control, you would have used the tables that are given in textbooks that invert the Laplace transforms, but you would have never been told how that is done. But that is actually done using the help of the residue theorem. Okay, so not just the Laplace transform, sometimes the inversion of Fourier transforms also involves evaluation of integrals. Okay, so we'll of course go step by step. So this module is only about several examples, right? So the first example is one of the simplest that we can think of. Suppose I have integral 0 to infinity dx upon 1 plus x squared, right? X is real. Okay, so this is a real valued integral, and this appears to have little or no connection with contour integrals that we have been discussing. So whenever you are faced with a real valued integral, you first say that instead of dx you have to convert it suitably into a complex valued function. So here I can say it is let's think of f of z as 1 over 1 plus z squared, and let's consider the integral dz by 1 plus z squared. Okay, now again the integral is about the real axis, right? It's not about it's going from x is equal to minus to plus infinity. This is the real axis, this is the imaginary axis, right? So this appears to have little again to do with a contour integral. Now the trick in evaluating almost all the integrals using the residue theorem is to somehow bring a contour into the picture, and make sure that suppose I have this same problem that we are discussing. Instead of x is equal to plus infinity to minus infinity to plus infinity, let's imagine that you are going from minus r to plus r in the limit. Eventually we'll take the limit r going to infinity, right? Now, so the contour that I'm going to choose is along the real axis from minus r to plus r. It's not a contour yet, but I'll close it like this. I'll go off the real axis into the imaginary axis and then come back to the point. So now this becomes a closed contour, right? This is not this is no longer sorry about this. Okay, let's just erase this. Okay, this is the imaginary axis. Okay, let's take this to be the contour. See, it's a closed contour, right? And it is off the real axis as well. So the key idea, we do not want this part anyway, but the key idea is to choose the contour such that semicircle that goes to infinity contributes basically 0. That's the trick. Okay, so somehow you close the contour, right, in the complex plane and use the residue theorem, because we know that the residue theorem can be used only for closed contours, right? Now the moment you draw this contour, the first thing you have to realize is that 1 over 1 plus z squared can be written as so 1 over 1 plus z squared is nothing but 1 over z plus I times z minus I. So there are two poles, a pole here and a pole here, I and minus I. Okay, these are the two poles. You might ask the question, why have I closed the contour on the positive imaginary axis and why not on the negative imaginary axis? I will show that it can be done as well, but care has to be taken so that the way in which you are closing the contour should ensure that the contribution from this part, the semicircular part of the contour, should essentially go to 0. Okay, that is the key idea in general, but in this particular example you might as well go above or below, as I will show. But in general the idea is to choose the contour, the semicircular contour, such that the contribution from that piece to that integral is 0. Okay, so let's call this contour C1, because I'm going to call the one with goes in the bottom side, the negative side of the imaginary axis, as C2 later. Okay, so how do we do this? Integral over C1 f of z dz is nothing but limit r tending to infinity minus r to plus r f of z dz plus integral over the semicircle with r going to infinity. Okay, the same f of z dz. Yeah. Now let's first deal with this part, right? Let's first deal with this part. Okay, now in order to understand this, in order to understand this part, let's think of z as r e to the I theta, because you are on the circle anyway, right? And then let's write our integral is 1 over 1 plus z squared, right? And in the limit when r is very very large, okay, limit capital R going to infinity, r I d theta e to the I theta upon 1 plus r squared e to the 2I theta. I'm just writing 1 plus z squared, right? In the limit when r goes to infinity, you can neglect this 1 compared to this term, right? And this essentially boils down to, as r goes to infinity, this will be limit r going to infinity. This r will cancel 1 r, and then e to the I theta will cancel 1 of it, and so on. So it will be I d theta upon r e to the I theta. Okay. Now, as r goes to 0, 1 over r goes to infinity, 1 over r goes to 0. This integral will tend to 0 as r goes to infinity. So the semicircle part doesn't contribute, right? So essentially we are interested in the limit r going to infinity minus r to r f of z dz, but that is nothing but the integral over the contour C1 of f of z dz. Now we know how to do this integral using residue theorem. This is nothing but 2 pi I times sum of the residues, right? How many poles are there within this contour? You have only one pole at z is equal to I. So the residue is 2 pi I times the residue at z is equal to I. That's nothing but 2 pi I times limit z going to I, z minus I times 1 over z plus I times z minus I, right? And these two things cancel, and then this simply becomes alright, and this simply becomes pi. So limit minus infinity, if I just say that this is along the z axis, so this z becomes this is along the real axis, right? Z becomes x along the real axis. Therefore you will get minus infinity infinity f of x dx is pi, or minus infinity to infinity dx upon 1 plus x squared. That is what is f of x is pi, right? It's a very neat way of obtaining the integral, right? Suppose you might ask the question, all this is fine, what if you choose the other contour? So let's quickly show what happens if you go in the opposite, if you choose the contour such that you are in the, this is minus r, this is plus r. Now I'm going clockwise. This is a semicircle. Sorry about the quality of the drawing. Oh, sorry. This is a contour C2. This is importantly a clockwise contour. It goes clockwise, unlike the previous one which goes anti-clockwise. Okay. Now the poles are again the same because the function is the same, right? So now what you will get is integral C2 f of z dz. Right. Now here again you can show that in the bottom side also it is the semicircle is not going to contribute. So here you will have, this is nothing but, so basically this is the same as what we want, minus infinity to infinity f of x dx. Now this is minus 2 pi I. Why is there a minus sign? Because this contour is clockwise, right? Whereas the residue theorem is traditionally for anti-clockwise. Usually we take the contour anti-clockwise, but here it is going clockwise. Okay, minus 2 pi I times residue of the function at z is equal to minus I is minus 2 pi I times the residue of the function is obtained by taking z is equal to minus I limit z plus I upon 1 over z minus I z plus I cancels. As z goes to minus I, you will get a minus 2i which cancels to give pi. So again you get the same answer, minus infinity to infinity dx by 1 plus x squared is pi. So this is again a neat way of solving a real integral using the residue theorem. Okay. So now if let me see if there is one thing that I forgot to mention when I started off this, right? So here, sorry about this, here the integral is from 0 to infinity, right? This is also from 0 to infinity, but because it's an even function, what is an even function? F of x is f of minus x. So I can write this as half of minus infinity to infinity dx initially to begin with. Okay, and let's say not this here, and from here I proceed to here. Okay, so originally we wanted just 0 to infinity, that is pi by 2. Okay, okay, so that is the, now there is one note regarding the identification of residues. It's a very important note. Suppose we say that the residue is the coefficient of 1 over z minus z naught in the Lorentz series of a function f of z, right? Series. Now suppose I have a function of the form 2z minus 4. I should write it in the 1 over z minus z naught form. This is like twice z minus 4 upon 2. This is 1 over 2 upon z minus 2. So now the residue becomes simply 1 over 2. It's a coefficient of 1 over z minus 2. This is the residue. So if you have the denominator in this form, you have to convert into this form. Okay, only then your answer will be, it will be easy for you to identify the residue. Okay, now let's do one more example. Here I am interested in evaluating the contour integral e to the I z by 1 plus z squared dz. Now C is a unit circle, but I am going to consider different unit circles. just to illustrate. Okay. Okay, so I'm going to now show you this integral, evaluation of this integral, where C is a unit circle, but it's placed at different points in the complex plane. So let's first take one of the points that we are going to, one of the contours. Suppose C is a unit circle about the point. Let me just first move this and then, okay. Okay, C is a unit circle about the point 1. About the point z is equal to 1. Okay. Now, what is the value of this integral for this contour? Now, if this is the contour C, okay, the radius of this contour is 1, and it's centered about z is equal to 1. What is the value of this integral? Now, the only thing you have to know is the residue theorem. This is I. The poles of this function are I and minus I. Okay, the poles are again I and minus I, right? So within this unit circle there are no poles. The function is analytic. Therefore, you can say that for this contour e to the I z by 1 plus z squared is 0. So you don't have to do any, you do anything, you can just almost by inspection you can identify the answer, right? Now let's take another circle. Okay, let me first draw the circle and then draw the coordinate axis. Okay, let's assume this is our circle. Let me move this a bit. Okay, let's say it's now centered about z is equal to I. This is the contour C, the radius is unity, right? Now what is integral? What is integral? dz e to the iz by 1 plus z squared, right? Now what you have to do is you should write this as integral e to the iz dz by z plus I times z minus I. Now you have to calculate use the residue theorem. You have to calculate the residue of the function at z is equal to I is nothing but limit z equals or z tending to I, z minus I times e to the I z by z plus I, z minus I. Okay, these two cancel, and then if I put z is equal to I, I'll get, so this is I times I is minus 1 e to the minus 1 upon 2I. This is the residue. Now using the residue theorem, the integral dz e to the iz by 1 plus z squared is nothing but 2 pi I times e to the minus 1 by 2I. The 2I cancels, you will get pi over e. Okay, that's the answer for this integral. So it is, sorry about this, it's that simple. If I were to consider or include the other pole in the contour, let's see. Okay, okay, now let's say this is my contour and this is minus I. Again, it's a circle of radius 1, right? Here now the integral becomes e to the iz dz upon z plus I, z minus I is nothing but 2 pi I times the residue. Now I have to multiply by z plus I and then put z is equal to I. If I put z is equal to z is equal to minus I, right? Okay, let me just do this. 2 pi I times z tends to minus I, z plus I e to the I z by z plus I, z minus I. right? Now these two things will cancel. If I put z is equal to minus I, you will get a plus e, and then you will have a minus I, so there will be a minus 2i which cancels with the 2i to give minus pi. So you get different answers depending on where the contour is placed. Again, this is something not new, but I thought you should understand how this works. Suppose I am interested in this integral cos x. This is a completely real valued integral. Suppose I was interested in this. Now cos x is nothing but a real part of e to the ix, right? So I can write this as integral. Now first thing that we should understand, this is both cos x and 1 plus x squared are even functions. So I can first do this as okay. Now let's say I'm interested in minus infinity to infinity. Let's not worry about 0 to infinity, right? This is our, so we first say this is nothing but this is the real part of e to the ix by 1 plus x squared dx. Now I am changing this x to z, a complex valued variable, 1 plus z squared minus infinity to infinity, right? Now I have evaluated this just now in the previous problem, right? I have just evaluated this in the previous problem. Now the only thing is, okay, let me elaborate this a little bit, right? We are interested in minus r to plus r as r goes to infinity. Now I'll of course choose a semicircle in the upper half, okay? Why am I choosing a semicircle in the upper half? Because e to the iz, if z is x plus iy, is e to the ix times e to the minus y. So this is x real part and this is y imaginary part. If I close the upper half, the integral over the semicircle will decay exponentially to 0, so that will not contribute. Okay, that's the reason why I'm choosing the upper half, right? So if I were to do this, now again I have only one pole at z is equal to I, so I know what the residue is. So this integral, this contour integral, let's call this contour C, e to the iz by 1 plus z squared, is nothing but minus infinity to infinity e to the iz by 1 plus z squared dz, because this piece doesn't contribute because it goes to 0, right? But we know what this is. We just derived this over a unit circle, but it doesn't matter as long as the contour encloses only that singularity. The answer is independent of the shape, right? So this is pi upon e. Now I can split it into a real and imaginary part, cos x by cos z by 1 plus z squared dz plus I minus infinity to infinity sin z by 1 plus z squared dz is pi by e. Now you have to equate the real and imaginary parts on both sides. That means that minus infinity to infinity cos x by 1 plus x squared is equal to pi by e, and minus infinity to infinity sin x by 1 plus x squared is equal to 0. Okay, this is how one uses the residue theorem even to evaluate real valued integrals, although there is no obvious connections between a real valued function and the residue theorem. This is very, very powerfully exploited in many applications. Okay, now there is one corollary of the residue theorem which we just showed in the last module. It's called the Cauchy's integral formula. Okay, now that was for if I had a function f of z by z minus z naught, and if f of z is analytic inside C, then this is nothing but f of z naught. Now you can generalize this to higher orders as well. Suppose I say f of z by z minus z naught the whole squared evaluated about C, where f of z is analytic within C, then you can say that this is proportional to, or this is equal to, f prime of z naught. Okay, these are all examples of the Cauchy's I forgot the 1 over 2 pi I, so obviously the 1 over 2 pi I is there. Now you can argue many ways. One simple way to go from this expression to this expression is differentiate both sides with respect to z0. See, remember, in this integral z is the variable, z0 is a constant, so you can differentiate on both sides. You can pull the differential integral inside, and then you will find that this gives to this. And similarly for an nth order derivative, 1 over 2 pi I integral over a contour f of z by z minus z0 to the n plus 1 is related to the nth derivative of n of f at z0. Okay, so it's a generalization of the same formula. One example to illustrate this application of this theorem. These are all examples of Cauchy integral formula. One example is, suppose you are asked to evaluate this integral, cosine z by z cube dz. You simply have to use this formula. The contour is about a circle, unit circle about the origin, where within that cos z is f of z is analytic, right? So simply use this formula. Put n is equal to 2 because you have z cubed, it's n plus 1, 2 plus 1 is 3, and z0 is 0. So 2 pi I, I'm using the same formula. So I'm pulling the 2 pi I here times d squared by dz squared, right, of cos z evaluated at z is equal to 0. This is nothing but 2 pi I, right, by 2 factorial, because okay, this is, I'm sorry, the general formula has an n factorial sitting in the numerator. Okay, that is something that you should keep in mind, because this is in a Taylor series you will get all these factorials when you expand a function, right? It is that is coming in here, right? So this becomes 2 pi I by 2, because this n is 2, so that comes here, right? This is 2 factorial times minus 1. This is simply minus pi I. So you can evaluate integrals like this if you have higher order poles also, using a version of the Cauchy's integral formula. Okay. The last example that I'm going to discuss in this illustration of evaluation of integrals using the residue theorem is a rather tricky one. Okay, let me say again example. Suppose you are asked to integrate sine x by x from minus infinity to infinity. As usual, we will say that this is sine z by z dz. Okay, and instead of sine z, I will say that it is the imaginary part of e to the iz by z dz and minus infinity to infinity. Okay, the pole is at z is equal to 0, but the key problem or the key issue here is the pole at z is equal to 0. So you have to construct a contour like our usual sense. You have to go from minus r to plus r, then you have to go up or down. That of course depends on whether the contribution from the semicircle goes to 0. But the key thing is, now the pole is right in the contour. Previously in all the examples that we had, the pole was inside, right? Now the pole is right in the contour. So what you have to do is you have to modify the contour a little bit. Okay, you have to go from, sorry about this, you have to go from minus r to r in the following sense, right? You go like this, then you take a detour, you avoid the pole, and then go, and then take a semicircle back. Now I've told you many times, the semicircle back, the semicircle to close the contour is chosen above or below depending on the nature of whether you can ensure that the integral from that part is 0, right? That is very, very important. It's not always obvious that you have to close. So this is the pole. Okay, now right, so now why have I chosen the pole above? right? So let's just argue that we have e to the I z. Z is x plus iy. So e to the I z is e to the I x times e to the I times y, which is minus y. So when y is positive, right, on the upper half of the plane, this it decays to 0 exponentially in the upper half of the complex plane. Okay, so this means that it is correct to choose the contour in the upper half. If I had chosen in the lower half, then it would blow up exponentially, which is not desired, because you don't want to add to the problem, you want to solve the problem instead of compounding it, right? So now, so what we are trying to do therefore is, okay, now there's one small information that I forgot. This the radius of this semicircle is small r, so we are going to take the limit as capital R goes to infinity and small r goes to 0. So the contour e to the I z dz is comprised of 4 bits. The first bit is from minus r to minus small r, then you go around in a semicircle from minus r to plus small r, then you go from plus small r to plus capital R, and then you go around this semicircle, right? These are the 4 bits. So let me write this: minus r to minus r. I don't want to write all the details here. This is integral over the semicircle of radius r of the integrand plus capital R, right, to plus small r to plus capital R, and then the integral from over the semicircle, the anticlockwise semicircle. But we have just shown that this vanishes because it's exponentially decaying as you take the radius of the semicircle to infinity, right? So this is not relevant to us. Now if you look at this bit, right, if you look at this bit and this bit, put together, they combine and give, oops, I'm sorry about this. If I add these two in the limit as capital R goes to infinity and small r goes to 0, this really is the integral that we want. Sorry, by z, right? Okay, and because it's along the real axis, you can substitute z for x, right? So this is the integral we want. Now if you look at the left side, now within this contour, the contour that we have chosen, there are no poles because the pole is on the axis. So the left side is actually 0 from the residue theorem or the Cauchy's integral theorem, because this is analytic, right? So all I have is plus integral over the semicircle, smaller semicircle, right, of radius r, e to the I z by z dz is 0. So if I somehow evaluate this, I will get this, right? That is the trick to this problem. So how do I evaluate the integral over the smaller semicircle, right? So the integral over the smaller semicircle, that's what we are interested in, right? So integral e to the I z by z dz is, I use z as r, small r e to the I theta, right? So dz is r e to the I theta I d theta, right? So if I take dz by z, I'll get I d theta, right? Now therefore e to the I z, okay, now as r goes to 0, z is r e to the I theta, right? R goes to 0, e to the I z goes to 1. So as small r goes to 0, e to the I z goes to 1, because it's like e to the 0. right? So you are essentially left with minus pi to 0. So remember, you are going clockwise from minus pi to 0, right? Minus pi to 0 I d theta, that is nothing but, right, minus so this is simply minus I pi. Okay, sorry, theta is, sorry, this is plus pi. I'm getting, so remember that this is, theta is always measured with respect to the x-axis. This is pi, right? So this is plus pi to 0, therefore you get minus I pi. Sorry for this confusion. Okay, right. So now what we have shown therefore is the as per residue theorem, e to the iz by z dz is 0, but this is comprised of two segments, minus infinity to infinity e to the ix by x dx. Then this part over the smaller semicircle, which we evaluated to be I pi, is 0. That means minus infinity to infinity e to the ix by x dx is plus I pi. Now there are two contributions, real and imaginary. So the real part is minus infinity to infinity cos x by x dx plus I minus infinity to infinity sin x by x dx. This was the original integral we wanted, is I pi. The real part has to be 0 because it's purely imaginary on the right side. So I can conclude that cos x by x dx is 0, and equating the imaginary parts, I get sin x by x dx is equal to pi. Okay, this is a very, very neat way of doing this rather complicated integral. Now one thing that you might, one last point about, rather subtle point about this is the idea of what is called the Cauchy principal value. What this means is the following. Now if I just look at the function cos x by x, it blows up as x goes to 0, because as x goes to 0, right, cos x goes to 1, this goes as 1 over x, right? Yet even though this integrand is diverging, the integral, right, the integral is still converging. Okay, that is because you have the, now I'm plotting cos x by x as a function of x. The integrand diverges if I go from the positive side like this, but if I go from the negative side, it also diverges to minus infinity. So there is a cancellation of these two infinities in some sense, right? That gives rise to a finite value, that integral cos x minus infinity to infinity cos x by x dx is 0. Okay, these such things are called principal values, right? Because if I look at it partially, there is a divergence of these integrands, but still you are getting a finite value for the integrals. I can illustrate this with a simpler example. Suppose I say integral 0 to 3 dx by x minus 3 and integral 3 to 5 dx by x minus 3. These both are divergent because this integral is nothing but ln of x minus 3 from 3 x is equal to 0, but ln of 0 goes to infinity, right? Minus infinity, right? It's divergent. So to avoid this, right, instead of going from 0 to 3, we'll say we are going from 0 to 3 minus r dx by x minus 3, and if you do this, you will get ln x minus 3 0 to 3 minus r. This is ln r minus ln 3. Obviously this ln r will diverge as r goes to 0, right? But in the same vein, if I go from 3 plus r to 5 dx by x minus 3, I will again get a piece which is ln 2 minus ln r. If I add these two pieces, note that this plus ln r divergence will exactly cancel out this. So integral 0 to 5 dx by x minus 3 is well defined. It has a well defined answer, ln 2 by 3, right? And such integrals are called principal values or Cauchy principal values. Okay, so so this is all about showing you some a few examples that illustrate how to use the residue theorem to evaluate integrals of various types, right? So I'll stop here for this module and continue from here in the next module.